Voyager 1 is moving away from the Sun at about 17 kilometres per second, or 10.6 miles per second. That is fast enough to cross the distance from Earth to the Moon in a little over 6 hours. But 1 light-year is so much farther that, at Voyager's current speed, the journey would take roughly 17,650 years. That is not a prediction of where Voyager is going. It is simply a way to put the distance into perspective. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometres, or 5.88 trillion miles. Even after decades of travelling away from the solar system, Voyager has covered only a tiny fraction of that. So what would it actually take for us to cross 1 light-year? At one extreme, we can start with the speed of a spacecraft that already exists. Voyager shows us what current deep space travel looks like. But at that pace, a 1 light-year journey would last longer than all of recorded human history many times over. At the other extreme are proposals such as directed energy sails, which could in principle accelerate a gram-scale robotic craft to around 1/5 the speed of light. At that speed, 1 light-year could be crossed in about 5 years as measured from Earth. But those two numbers describe very different missions. 17,650 years extends the measured speed of a real spacecraft under simplified assumptions. 5 years describes a proposed flight by a tiny robotic craft that has never demonstrated that journey. It is not a passenger spacecraft, and the simple crossing time does not include the problem of slowing down at the destination. For people, that last part matters enormously. A real mission would have to accelerate, survive the crossing, protect the crew, and then shed enough speed to arrive, rather than simply fly past. The faster we try to make the journey, the harder some of those problems become. So there is no single answer to the question, how long does it take to travel 1 light-year? The answer depends on what is travelling, how fast it can realistically accelerate, whether it needs to slow down, and what we mean by actually reaching the other end. By the end of this video, you will understand why the same 1 light-year journey can produce answers ranging from thousands of years to only a few, and which mission requirements determine whether any of those numbers describe a real arrival. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. The name light-year can make 1 year sound like a voyage time, but it names a distance. The word year helps construct that distance. It does not say how long a spacecraft travels. Start with the speed used in the definition. Light in a vacuum travels at exactly 299,792,458 meters per second. That value is exact, rather than a rounded measurement. To turn that speed into a distance, multiply it by 1 Julian year. The seconds in the speed and the seconds contained in that stated duration pair up, leaving a length. Here, the speed and duration define the ruler itself. The result is about 9.4607 trillion kilometres. That is 1 light-year. The word about belongs with the kilometre figure because it is a shortened decimal expression of the resulting distance, while the speed of light in vacuum remains the exact value we began with. Using a Julian year also fixes which year convention belongs in this ruler, so the distance does not shift with whatever calendar year someone happens to have in mind. None of that assigns the same speed to a spacecraft. A lamp carried aboard a vehicle would still emit light, but the unit says nothing about how fast the vehicle carrying that lamp can move. Calling the destination 1 light-year away does not give the vehicle an engine, a route, or a way to reach light speed. Those would be separate physical claims, and the definition makes none of them. It also does not promise arrival after 1 year. A 1-year trip would require a particular account of the vehicle's motion, while the light-year supplies only the fixed length to be crossed. Questions about acceleration, slowing down, safety, and whether such a trip is feasible cannot be read out of the unit. We now have the ruler, about 9.4607 trillion kilometers from end to end. The travel time still has to be worked out from conditions the name never specifies. That long distance becomes easier to hold in your mind when the same ruler is marked in smaller pieces. The first mark is a light second. The distance light travels through vacuum in 1 second. The word second tells us which interval was used to make the measurement. It does not turn the result back into a duration. If 2 points are 1 light second apart, their separation is a distance just as surely as a separation stated in kilometres. A light minute extends exactly the same convention. Light's defined speed through vacuum is applied over 1 minute, producing a longer distance on the same scale. Nothing new has been added to the motion of light, and the name does not describe the performance of a spacecraft. It simply replaces a very large distance written in smaller units with the distance light covers during that stated interval. You can move from a light second to a light minute without changing what the ruler measures. The light hour is the next longer version of that same measure. Its name means the distance light travels through vacuum in 1 hour. The hour does not supply an engine, a flight plan, or a predicted arrival time for anything else. It only sets the length of this particular rung. A vehicle could cross that length more slowly, or under conditions that change its speed, but none of those details belongs to the unit itself. Light days and light years continue the sequence. A light day is the vacuum distance associated with 1 day of light travel, while a light year is the vacuum distance associated with 1 year. These names do not identify new kinds of objects or different forms of travel. They are longer marks made by extending one distance convention across longer stated intervals. So the light year can sit at the far end of a continuous scale rather than floating alone as an enormous number. Light second, light minute, light hour, light day, and light year all belong to one expandable ruler. The labels tell us how each fixed distance was defined. To turn any one of those distances into a trip time, we still have to place a particular traveller against the ruler and describe how that traveller moves. Once the traveller is named, the first calculation is simple. Time equals distance divided by speed. The distance is 1 light year, and the speed belongs to the traveller rather than to the ruler. For the comparisons here, the time unit is the Julian year. Keeping that convention fixed means 2 results can be compared without quietly changing what the word year means between them. But speed needs more than a number. It also needs a reference frame, the point of view from which the motion is measured. A craft can have one speed relative to its departure point, and a different speed relative to something else that is moving. If we leave out the frame, the same speed figure can describe different physical situations, so the division no longer gives a clear mission comparison. We have to say what the craft is moving relative to before placing its speed beneath the light-year distance. Direction belongs in the description as well. Motion toward the destination reduces the remaining distance. Motion away from it does not. Motion in some other direction cannot be treated as though all of that speed carries the craft straight along the route. A usable comparison, therefore, names a craft moving in a stated direction, measured in a stated frame. Only then does the speed describe the traveller we mean. Even with those conditions supplied, distance divided by speed gives a constant speed comparison. It treats the craft as if it covers the stated distance at that speed throughout the calculation. It does not describe the launch, the time needed to accelerate, or the time and distance needed to brake for a stopped arrival. It also leaves out the chosen route, the energy required, shielding and navigation. Each of those could change a real trajectory, but none is contained in the bare division. So a duration produced this way is conditional. It answers how long 1 light year would take for a named craft at a defined constant speed in a defined reference frame and direction, under the exclusions we have stated. It is a clean way to test familiar speeds against the same distance ruler. It is not a forecast for a complete voyage. That same ruler has to stay fixed for every comparison, 1 light year from start to finish. If we shorten the distance for one traveller, or choose a different endpoint for another, their times no longer answer the same question. Holding the distance constant removes that confusion. Each result then tells us what a different stated speed does to the time needed to cover exactly the same span. The arithmetic changes in only one place. Time equals distance divided by speed, so a higher speed produces a shorter crossing time and a lower speed produces a longer one. But the speed entered into that division is a condition, not a design for an engine. It says nothing about what provides the thrust, how much energy the craft needs, whether it can reach that speed, or how it survives while moving that fast. A shorter answer from the division cannot supply any of that missing evidence. Even the word crossing can describe several different outcomes. A craft may pass the 1 light-year mark while still moving, which is all a bare constant speed calculation requires. A flyby may continue past its target without stopping. A stopped arrival has to lose its speed near the destination, so it needs evidence for braking as well as acceleration. Calling the same duration a human mission adds further requirements. People must remain alive and healthy, and the craft must keep its life support systems working throughout the trip. These outcomes cannot be exchanged just because their routes cover the same distance. The proposed sail, travelling at 0.2 times the speed of light, shows why the label matters. That case describes an ideal, gram-scale flyby crossing. Its division may give a fast time across the fixed ruler, but it does not establish a propulsion system for a crewed craft or a way to stop one at the far end. With the ruler held steady, speed comparisons remain comparable, while the mission claims remain separate. The distance stays at 1 light-year. Now give the traveller a constant walking pace of 5 kilometres per hour, or about 3.1 miles per hour. The method does not change. Travel time equals distance divided by speed. At that pace, the crossing takes roughly 216 million years. It is a rounded scale calculation, but the scale is already enough to put a familiar human movement against the fixed ruler. Only the speed has changed. The light year has not been shortened, and the arithmetic has not been adjusted to make walking look especially slow. Each hour accounts for another 5 kilometres, while the full 1 light-year distance remains the distance that must be covered. Dividing that distance by the constant pace produces the enormous duration. If the speed remains fixed, this is how long the distance requires. Walking is something your body understands without an instrument panel. You can feel the effort of maintaining a pace and judge a nearby trip in terms of time spent moving. That personal sense of travel stops being useful when the destination is 1 light-year away. 216 million years is beyond any experience a person can bring to the comparison. The mismatch appears before anyone chooses an engine, designs a spacecraft, or asks how much fuel it would carry. Astronomical distance has already overwhelmed bodily motion. This does not make walking a physical proposal for crossing space. There is no traversable path laid out between the starting point and the destination, and no account here of what a human body would need along the way. The calculation provides no life support system, no protection from vacuum conditions, and no plan for sustaining motion across the crossing. It also leaves acceleration aside by assigning the walking pace from the start and holding it constant throughout. The rounded duration belongs to a scale comparison rather than an actual itinerary someone could follow. Give the same division a constant road speed of 100 kilometers per hour, which is about 62 miles per hour, and the answer changes sharply. 1 light year divided by that speed comes to about 10.79 million years. The calculation gives the car its full speed at the start and holds that speed for the entire crossing. It does not include time spent slowing down, stopping, or getting back up to speed. This is simply distance divided by a fixed rate, with 100 kilometers, or about 62 miles, covered during every hour on the mathematical clock. Compared with the walking result, that is a huge reduction in time. Raising the speed from a body's pace to road speed cuts away a vast stretch of the arithmetic. Yet the answer has not left the same broad category. It is still measured in millions of years. Even after replacing each slow step with continuous travel at 100 kilometers per hour, a single light year still takes about 10.79 million years. The car itself cannot be carried over from this comparison into space. Road vehicles depend on a surface and on the physics that let a road vehicle operate against that surface. They also depend on an atmosphere and on terrestrial operating conditions. The empty distance between stars does not supply a road, and this division supplies no substitute for one. It gives us no interstellar propulsion system, and no physical plan for maintaining the assumed speed through vacuum. Those are separate problems. Here, the road speed is only a familiar mark on the ruler, used to test how much the duration changes when the comparison moves well beyond walking pace. The increase removes a great deal of calculated time while leaving millions of years intact, as speed can clarify the size of a light year even when the vehicle associated with it has no place in an interstellar mission. At a constant 900 kilometres per hour, or about 560 miles per hour, the time falls to about 1.20 million years. That is the distance of one light year divided by the stated speed, with the speed held unchanged for the entire calculation. There are no stops hidden in that result and no slower stretches. Even under that clean assumption, the answer is still measured in millions of years. Moving from 100 kilometers per hour to 900 multiplies the familiar speed by 9. For travel on Earth, that increase changes what can be reached within the same span of time. Across one light year, it cuts the calculated duration by the same factor, from the road scale result of 10.79 million years to about 1.20 million. The reduction is large, but it does not move the answer into thousands of years, centuries, or a human lifetime. You can make the familiar transport 9 times faster and still remain on the million-year scale. That number describes a distance and speed comparison, not a proposed flight. It assumes 900 kilometers per hour from one end of the light year to the other, so it does not tell us how a vehicle would reach that speed, maintain it, or follow a workable interstellar path. And an aircraft's airspeed should not be treated as a spacecraft's change in velocity. Those are different physical descriptions, even if the same speed can be placed into the simple time equation. The aircraft itself also brings the familiar transport comparison to its limit. An aircraft operates by using the surrounding air. Interstellar space does not provide that working environment. So the vehicle that makes 900 kilometers per hour familiar on Earth is not a propulsion model for crossing a vacuum. Its speed sharpens the scale, but its method of moving cannot be carried into the problem with it. That measured velocity can go into the same equation as walking, driving, and flying. In every case, the distance stays fixed at 1 light year. We divide that distance by an assumed speed, and the result is a travel time. The method has not changed as we have climbed the speed ladder. Only the speed placed beneath the distance has changed. That is why the ladder is useful. It lets you feel what happens to the time when the speed arises, while keeping the destination exactly where it was. But the calculation says nothing about how a traveler reaches any of those speeds. The road speed result does not test a road vehicle, and the aircraft result does not make an aircraft into an interstellar craft. They are scale comparisons produced by division, not evidence that one propulsion system is better than another. A real spacecraft comparison has to begin with the source of its velocity. We need to know what gave the craft that motion, rather than treating the speed as a number that appeared on its own. We also need its reference frame and its direction. A measured velocity is always a velocity relative to something, and a high value does not by itself tell us that the craft is moving along the route we want. Then the conditions of the mission have to join the arithmetic. The craft must accelerate to its travel speed, and a complete route would need a braking plan rather than assuming it can arrive while still rushing past its destination. The vehicle and anything aboard it would also have to survive the conditions involved in gaining and sustaining that motion. None of those requirements can be established by dividing 1 light year by a stated speed. A physical spacecraft comparison therefore needs more than the largest number available. It needs a measured velocity together with the trajectory that produced it, what accelerated the craft, what the measurement is relative to, and where the craft was actually going. NASA's Parker Solar Probe gives us a measured spacecraft record with a very large number attached to it. At its closest solar approach, the probe reaches about 692,000 kilometers per hour, or about 430,000 miles per hour. NASA reports that value as an approximate peak. It is a speed the spacecraft has actually reached, rather than a proposed cruising speed for a vehicle that has never flown. That distinction gives the comparison a firm starting point. Parker's number comes from a real mission and a real measurement. but the word peak is doing important work. It tells us that this is the highest speed associated with a particular part of the probe's motion, not a promise that the same speed continues indefinitely. The setting of that peak is just as important as the number. Parker is on a Sun-focused mission, and the record occurs during its closest approach to the Sun. Its path and the location of the measurement belong together. If we lift the speed away from that geometry, we lose the physical circumstances that made the record meaningful. The probe's measured motion near the Sun therefore cannot be relabeled as a steady outward cruise between stars. Nothing in the record says that Parker holds 692,000 kilometers per hour after the close approach, or that this motion carries it toward a chosen star. The measurement remains valid. Its meaning remains tied to the trajectory on which NASA measured it. A travel time answer needs more information than the fastest instant on that trajectory can supply. Speed tells us how quickly position is changing at a given time. A trip also needs a direction, because motion toward the Sun, around it, or along some other part of a path cannot automatically be counted as progress toward an interstellar destination. It needs a duration as well, since a peak lasting only part of a trajectory is different from a speed maintained across the full distance. And it needs an actual destination connected to a defined outward route. Parker's record supplies none of those missing pieces by itself, so the measured peak can establish how fast a spacecraft has gone under its own mission conditions, while its solar approach geometry prevents that number from serving directly as the speed of a 1 light-year flight. Parker's solar probe reaches its greatest speed deep in the Sun's gravity during a close approach. That setting is part of the record, not a detail we can remove from it. As Parker drops close to the Sun, solar gravity gives it the conditions for that brief, very fast motion. The speed belongs to a particular place and part of an orbit. It isn't a stored cruising speed that Parker could simply turn away from the Sun and carry unchanged toward another star. Momentary velocity describes motion at one point on that orbit, with both a speed and a direction. A star-bound trajectory would need a different geometry, motion arranged to go outward toward the chosen destination. Parker's velocity near the Sun follows the path of its close approach, so even a genuine record at that instant doesn't define how the spacecraft would depart the solar system. Extending the number along an imagined straight line would silently replace Parker's real path with one the mission has not flown. The line may be easy to draw, but the record itself doesn't supply it. A real route would have to begin with a defined launch and say which gravity assists shape the path. It would also need an energy plan that produces the required motion, rather than treating a peak created deep in solar gravity as if it were available everywhere. Then the trajectory would have to point toward a specified target. Those choices belong together, because changing the launch or an assist changes the geometry, while changing the target changes the direction the whole route must serve. No such interstellar departure architecture has been established for Parker here, and the close approaches were never presented as failed attempts to create one. So if we temporarily let Parker's record speed run straight across 1 light-year, we must label the result for what it is, a counterfactual calculation, not a Parker mission plan. It can show what careless use of the record number produces, while leaving unanswered how any spacecraft could acquire that outward path, sustain the assumed motion, and aim it at the destination. With that label in place, the division is simple. Take 1 light-year and divide it by Parker's peak speed, as though that speed carried the spacecraft directly away from us for the entire distance. The result is about 1,562 years. Rounded more loosely, that is roughly 1,560 years. It is an eye-catching answer because the calculation itself is valid once we accept the conditions placed inside it. Those conditions are doing nearly all the work. The division takes a peak reached near the Sun and substitutes a perfectly aimed outward cruise. In this imagined case, Parker is already moving in the required direction, and its speed remains constant from the starting point to the far end of the light year. A moment at perihelion has been stretched into more than 15 centuries of uninterrupted travel. Parker's record does not supply that path. The peak belongs to the spacecraft's actual motion close to the Sun, where its trajectory is not the straight interstellar line assumed by the arithmetic. So the counterfactual changes both the direction and the duration of the recorded motion before it produces the 1,562-year result. It answers a made-up constant speed problem, not the mission problem we began with. The number works best as an error detector. It shows how a genuine speed record can become a false travel claim when the route is removed. No extra precision can recover the missing trajectory, acceleration, navigation, braking, or operating life. So roughly 1,560 years is not Parker's travel time, a forecast, the fastest plausible trip, or a route to any chosen star. It is the answer to a deliberately inapplicable question: how long 1 light-year would take if Parker's perihelion peak became perfectly directed, constant outward motion. A comparison that can speak to the title needs a spacecraft that is actually traveling outward, with the reference frame of its stated speed made clear. Voyager 1 gives us that comparison. It is already traveling outward, so its motion has the direction that Parker's close pass did not. The mission's cited velocity is measured relative to the Sun. That reference frame matters, because speed is always speed relative to something, and here the something is our Sun. The figure therefore describes Voyager 1's outward motion through the solar frame. It does not turn the spacecraft toward a selected star, supply a route, or promise that the same velocity will continue unchanged all the way to an arrival. Voyager 1 also brings a different kind of evidence, a mission history built in deep space. Communication has continued across that setting, and the hardware has remained in service for a long time. Those are things the spacecraft has actually done. They make it a more relevant benchmark than a brief peak speed reached near the Sun, because the comparison now joins outward travel with some demonstrated persistence. We are no longer borrowing a momentary speed from a maneuver whose direction and conditions were wrong for the trip. We are looking at a spacecraft whose motion is outward and whose working life has extended far beyond a short test. But the evidence has a firm limit. A long-lived spacecraft is evidence that machines can endure beyond their planned encounter with a planet and can continue communicating in deep space. Its record covers only the time it has survived so far. It cannot demonstrate that the same hardware would remain functional for thousands of years, much less establish a working vehicle for 17,000 years. Continuing to receive from Voyager 1 does not make its lifetime indefinite. It gives us an observed history with an endpoint that has not yet arrived. The two claims must remain separate. Voyager's velocity can be used as a solar relative starting datum without turning its survival record into an assumption of equal duration. Holding a speed constant for the arithmetic says nothing about whether the transmitter and the rest of the hardware could last that long. For the arithmetic, NASA gives Voyager 1 a speed of 17.0 kilometers per second relative to the Sun. In miles, that is 38,026.79 miles per hour. NASA dates that value to August 21st, 2024. Those details belong together: the number, the object it is measured against, and the date on which the source reports it. Relative to the Sun tells us what the number actually describes. Speed is always measured from some chosen reference. A passenger can be still compared with a seat while moving rapidly compared with the ground, and neither measurement is wrong. They answer different questions. Voyager's quoted speed works the same way. The approved comparison asks how long 1 light-year would take if we use its motion with respect to the Sun. So the solar relative value is the one that can be placed into that division. Substituting a speed measured in another reference would change the conditions while leaving the units looking familiar. The date places a second limit around the input. August 21st, 2024 is when the cited NASA value applies in this comparison. Holding it constant is a condition of the arithmetic, not a claim about every earlier or later point in Voyager's flight. And holding the number constant does not convert Voyager 1 into a mission aimed at a destination 1 light-year away. It does not describe a planned route, predict the spacecraft's future path, or promise that its systems would operate until the imagined crossing ended. We have already separated the probe's observed survival from any assumption that its hardware could last across such a span. This input leaves that separation intact. It asks a narrower conditional question. If something covered 1 light-year at the cited solar relative speed, with that speed treated as constant for the arithmetic, how much time would the distance divided by speed produce? NASA's dated figure now gives that calculation a fixed starting condition, without turning the result into Voyager's itinerary. With that rate fixed, the other half of the calculation is the distance. 1 light-year is 9.4607304726 trillion kilometres. That value comes from taking the exact SI speed of light and asking how far light travels during 1 Julian year. So the light-year is the length in this division, not a measure of time, even though a year appears in its name. The rate comes from NASA's dated figure for Voyager 1, 17.0 kilometres per second relative to the Sun. We keep that measured value exactly as cited. We don't replace it with the speed the probe might reach later, or with the speed chosen to make the arithmetic easier. The comparison, therefore, has a fixed distance and a fixed rate drawn from two clearly defined measurements. Now divide 9.4607304726 trillion kilometres by 17.0 kilometres per second. The kilometres cancel, leaving a duration in seconds. Converting that duration into Julian years gives 17,649.6 years. That is the approved constant speed result before we make it easier to say aloud. Rounded without changing its scale, it is roughly 17,600 years. You can read that number in a very narrow way. If something covered a 1 light-year distance at Voyager 1's cited solar relative speed, the division says the crossing would take about 17,600 years. The speed would have to remain constant for the entire calculation, and it would have to stay aligned with the direction needed to cover that 1 light-year distance. If either condition changes, this particular quotient no longer describes the crossing. The result is a conditional distance over speed comparison, not a forecast for Voyager 1 or a route it was meant to follow. Voyager 1 has moved beyond the immediate setting of the planets, but departure alone does not make it a mission to a selected star. It was not placed on a booked route with a chosen stellar destination at the end. The conditional crossing time can still compare its outward speed with 1 light-year, as long as the speed and direction stay fixed in the calculation. It cannot supply a mission plan that Voyager never had. The probe can communicate with Earth now, but that present success belongs to the mission as it exists now. It does not show that a signal could still be exchanged across 17,600 years. Extending today's communication into that distant time would add a claim the evidence does not establish. So the measured motion and the working radio link answer two limited questions. Voyager is moving outward, and controllers can communicate with it at present. Neither answer promises a working connection for the full crossing. A true outward mission would need a destination chosen before launch, then guidance capable of keeping the vehicle on the required path. It would also need a payload suited to the task waiting at the other end. Merely passing through the distance would count as a crossing, but it would not guarantee that the payload reached the intended place or remained able to do anything useful there. Targeting, carrying the right equipment, arriving, and operating are separate requirements, even when one's speed has made the arithmetic look simple. Arrival also needs a precise meaning. A vehicle that passes a destination at high speed has reached its vicinity in one sense, yet it has not stopped there. Capture requires a braking architecture, and that requirement changes the mission from a pure distance divided by speed exercise. A cited photon sail model can describe one proposed way to make a crossing, but its modeled speed is not a universal limit for every possible vehicle. Comparisons with a faster design, therefore, have to identify what actually produces the extra speed, while still accounting for direction, payload, braking, and operation at the destination. Without those conditions, a departure time is being mistaken for a complete mission. A shorter crossing time means the vehicle must gain more velocity before it can cover the distance. That gain cannot come from changing a number in the travel calculation. Some physical mechanism has to push the vehicle and produce the required change in motion. The mechanism could be carried aboard, or energy and momentum could be supplied from outside, so there is no single propulsion rule that describes every possible design. Either way, a claimed speed has to be connected to whatever produces it. Until that connection is made, the faster voyage is only a faster assumption. For a rocket carrying its own propellant, the payment includes reaction mass. The rocket throws that mass one way, so the rest of the vehicle gains velocity the other way. As propellant is expelled, the vehicle becomes lighter, but the propellant used later had to be accelerated earlier along with the payload, tanks, engines, and all the propellant still waiting to be burned. This is why the ideal rocket equation connects a requested velocity change with the exhaust velocity and the ratio between the rocket's starting mass and its mass after the burn. It is a relation between mass and exhaust under idealized conditions. It does not provide the tanks, choose a route, account for every loss, or turn that relation into a complete working vehicle. And it does not govern a system whose energy or momentum is supplied externally in the same way. Arrival adds a second demand. If the vehicle accelerates to a high cruising velocity and reaches the destination still moving at that velocity, it has completed a fast flyby, not a stopped arrival. To remain there, it must remove velocity through some physical braking method. A carried propellant rocket may therefore need reaction mass for slowing as well as speeding up, with the braking propellant carried during the outward acceleration. The exact mission design can change how those burns are arranged, and another propulsion architecture may pay differently, but the velocity still has to be removed if stopping is required. The long crossing time from division is also a propulsion problem. Reducing it asks for a larger velocity change, whose relationship with exhaust velocity appears as a mass ratio. The ideal rocket equation connects that required change in velocity, usually called delta V, to two properties of the rocket. One is the speed of the exhaust leaving the engine, the other is the mass ratio. The rocket's initial mass, including its propellant, divided by its final mass after that propellant has been expelled. Delta V equals the exhaust velocity multiplied by the natural logarithm of that ratio. The logarithm is the part that changes the feel of the problem. If the engine's exhaust velocity is fixed, doubling the mass ratio does not double the available delta V. Each further increase in velocity requires another multiplication of the ratio between the full rocket and the emptied rocket. You can raise the exhaust velocity instead, but for a specified engine and rocket, that value is already part of the description rather than a free adjustment. The same relation can be read in the other direction. Begin with a desired delta V and a known exhaust velocity. Then invert the equation to find the mass ratio that the rocket would need. Once the specified rocket's final mass is known, that ratio determines how much initial mass must be present, and therefore how much of the difference must be propellant. This is how a request for more velocity becomes a requirement for more carried mass. That conversion is not proportional. Adding the same amount of delta V again calls for multiplying the mass ratio again, because the equation places delta V inside an exponential when it is solved for the ratio. The added propellant cannot be treated as a separate tank that provides a matching block of speed. It begins the burn as part of the mass the engine has to accelerate, along with the vehicle and a propellant that will be used later. This is an ideal mass and exhaust relation, not a complete mission design. By itself, it cannot tell us the mass of an unspecified starship, choose a route, describe the operating environment, or say whether the vehicle can survive and arrive as intended. It does tell us why a carried propellant rocket cannot treat fuel as a linear reserve of speed. If that rocket must gain velocity and later remove it to stop, each required change belongs in the delta V account, while the propellant reserved for braking is already included in the mass accelerated outward. That later change in velocity is easy to leave out when we talk about a ship's top speed. Before the ship can cruise, its rocket has to accelerate it from the velocity it had at departure to the velocity chosen for the crossing. The size of that required change is its outgoing delta V. Cruise speed describes the state the ship reaches. Delta V describes what the propulsion system must do to get it there. For a carried propellant rocket, that demand is tied to the exhaust speed and the mass ratio we have just followed. Reaching the far end of 1 light year does not necessarily mean arriving there in the mission sense. If the destination is moving at a different velocity, a ship that crosses the distance marker while still carrying its cruise speed will keep moving relative to that destination. A stopped arrival, therefore, calls for another velocity change, one that removes the relative speed left after the crossing. That braking demand belongs in the mission's delta-v account separately from the push that established the cruise. This changes what a travel time answer can claim. Dividing the distance by a named cruise speed can describe the time spent crossing at that speed, but it does not specify how the ship gains the speed at the beginning or loses relative speed at the end. Unless the calculation supplies acceleration and deceleration profiles, it leaves both boundaries open. The result may still be a useful line crossing time, but it is not yet the duration of a fully described trip that begins in one state of motion and ends stopped in another. Braking does not give every mission an exact factor of 2. The outward and inward velocity changes need not use matching profiles, and a propulsion design may handle them in different ways. The mission objective also changes the requirement. Crossing a point at speed asks less of the ship than matching the destination's motion. What remains fixed is the distinction. Gaining cruise speed and removing relative arrival speed are separate demands, and the burden each places on a rocket depends on the exhaust it can produce and the mass ratio needed for the required delta-v. The exhaust sets part of that burden because a rocket changes its motion by throwing mass away. Exhaust leaving faster carries more momentum for each amount of propellant expelled, so the vehicle can gain more delta-v. With slower exhaust, achieving the same velocity change requires the rocket to throw away a larger share of its starting mass. This is why exhaust velocity and mass ratio belong together. Mass ratio compares the fully loaded vehicle with the mass left after its planned propellant has been spent. The engine may provide the push, but the ratio tells us how much mass must be carried to make that push add up to the required change in motion. Payload sits inside the same accounting. The payload, tanks and rest of the vehicle must all be accelerated along with the propellant. If the payload grows, while the exhaust performance and mission stay the same, more propellant is needed to move it through the same delta-v. That added propellant has mass too, and it must also be accelerated. The required amount, therefore, depends on the complete vehicle rather than the engine considered by itself. The mission profile changes the answer again. A ship that only passes the destination can spend its available delta-v differently from one that must arrive with its relative motion removed. The acceleration schedule, the chosen trajectory, and the required condition at arrival determine the total velocity changes the propulsion system must supply. Changing any of those conditions changes the propellant calculation, even when the engine and its exhaust velocity do not change. So an engine name cannot be converted directly into a time for traveling 1 light year. 2 vehicles could use the same named engine yet carry different payloads, begin with different ratios of propellant to remaining mass, and follow different mission profiles. They would not have the same available delta-v or the same travel time. Before a duration can be calculated, we need the engine's exhaust performance, the vehicle's full mass account, the payload, the trajectory, and whether the ship must merely cross the destination or stop there. A carried propellant rocket is one complete architecture, and its result comes from those specifications together. That leaves a separate possibility. Supplying energy from outside the vehicle changes what the ship must carry with it. The outside supply could be directed light aimed at a photon sail. Light carries momentum, and when that light reaches the sail receives some of it. The push therefore comes from energy sent toward the vehicle rather than from a store of energy released entirely aboard it. This is a proposed light sail architecture, not a tiny rocket under another name. That change moves part of the mass burden away from the craft. A vehicle using carried propellant must accelerate the propellant and the equipment that contains and handles it until that propellant is used. With directed external light, the source supplying the energy is elsewhere, so the sail does not have to carry that entire supply along for the ride. The rocket equation has not stopped describing rockets. The sail has changed the propulsion arrangement that placed the carried supply inside the vehicle in the first place. The exception is specific, though. Receiving momentum from light does not tell us whether the sail can endure the heat associated with the directed energy, or whether its materials can keep working under the required conditions. It does not prove that the light can remain pointed where it must go, while the sail moves farther away. Those are separate engineering tests, and a proposal has to meet each of them on its own terms. Interstellar space adds other tests that do not disappear when the energy source stays behind. Dust can still meet a fast-moving craft along its path. Communication still has to work across the growing separation between the vehicle and the people or systems supporting it. Neither problem is answered simply by showing that external light can provide momentum. Arrival remains separate as well. A sail that can be accelerated outward has not, for that reason alone, been shown to break at the destination. Crossing a target region and arriving there at rest are different mission outcomes, while carrying people adds requirements beyond demonstrating a sail's motion. So a directed energy sail can remove part of one burden without establishing a stopped crewed trip across a light year. Any proposed system still has to be judged by its own specifications, its evidence, and the mission outcome it can actually deliver. Project Orion gives us a very different propulsion proposal to judge. It was a nuclear pulse concept, built around repeated nuclear pulses transferring momentum to a vehicle. Orion was not simply a name for a powerful engine, and it did not depend on a distant beam continuing to push as the vehicle moved away. The proposed pulses would act again and again, making this a distinct high-thrust architecture. This proposal also belongs to the history of engineering, not merely to fictional starships. NASA's historical account treats Orion as a real subject of technical work, and later reassessments returned to it as a case worth examining. Engineers seriously studied a way to use repeated nuclear pulses for propulsion. We can therefore inspect the architecture as an engineering proposal, ask what momentum it could provide, and examine the constraints attached to it. Calling it a serious case study gives the proposal its proper weight, without turning analysis on paper into hardware that completed a mission. The limit of the evidence is just as specific. Orion was not a flown interstellar vehicle. The approved record does not establish a crewed schedule for traveling 1 light year, and it does not support the familiar claims that attach a particular fraction of light speed or a particular number of years to such a trip. Those numbers may make the name feel like a ready answer, but they are not verified by the evidence we have here. Investigation and later reassessment establish that the concept received serious attention. They do not establish present feasibility, a launch plan, a route, or a demonstrated mission duration. Orion shows that engineers seriously studied an architecture intended to transfer momentum through nuclear pulses. The historical record supports that design study, not the claim that a human starship or scheduled 1 light-year voyage was nearly available. The legal setting needs the same precision. Orion is often described as though one word, banned, finished the story. The Partial Test Ban Treaty gives us something firmer and more limited than that shorthand. It prohibits nuclear weapon tests and other nuclear explosions in specified environments, including outer space. For a propulsion concept built around repeated nuclear explosions, that prohibition is a direct constraint. It belongs in any serious account of the design. But the treaty's operative wording has a defined scope. It tells us what kind of act is prohibited, and names environments where the prohibition applies. It does not, by that wording alone, answer every question that could be attached to every imagined vehicle. A hypothetical architecture may raise questions about its exact design, where an operation would occur, which jurisdiction would govern it, and which legal obligations would apply. Saying banned by treaty skips those facts before they have even been supplied. That distinction also prevents one propulsion idea from standing in for all the others. Orion was an explosive pulse concept. Nuclear explosions would transfer momentum to the vehicle. The treaty restriction described here concerns nuclear weapon tests and other nuclear explosions in the specified environments. It should not be stretched into a blanket conclusion about every technology that carries the word nuclear, because those technologies need not share Orion's explosive mechanism. The evidence supports the stated restriction, not a universal verdict on nuclear propulsion. Nor does this source settle the present law for a real mission. Treaty membership, national law, licensing, the factual details of a proposed architecture, and its operational safety would all require evidence beyond the treaty claim available here. Those are proposal-specific questions, and answering them would mean examining the actual parties, hardware, location, and planned acts. Without that record, a final legal judgment would be guesswork rather than analysis. So a nuclear pulse proposal has to survive more than an engineering calculation. Its technical design determines what the vehicle would physically do. Its operating plan determines where and how those acts would happen, and the applicable legal rules constrain which operations could proceed. None of those inquiries can substitute for the others. The treaty supplies one exact boundary around nuclear explosions in places that include outer space, while the architecture's remaining mission requirements still have to be stated and tested on their own terms. That leaves the engineering case to stand on its own. Calling a proposal nuclear pulse propulsion identifies a family of ways to supply momentum, but it still does not identify one vehicle. A particular architecture would need a defined launch location and a defined pulse unit design. Until those choices are made, the name tells us too little about what would be built, where it would operate, or which physical and operational limits would apply to it. The vehicle itself then has to be accounted for. Its mass affects what the propulsion system must move, while its acceleration determines how the payload or crew experiences the change in speed. If people are aboard, radiation is another mission variable that must be addressed rather than absorbed into the engine label. These questions remain open even if a proposed system can produce high thrust, because thrust describes only part of what the vehicle can do. A specific impulse answers a different part of the propulsion problem, but a strong value there cannot supply the missing mission design either. It does not choose the vehicle mass, settle the radiation problem, or say what acceleration a crew could undergo. And neither high thrust nor specific impulse, by itself, establishes a schedule for carrying people across 1 light year. Turning either performance claim into a travel time would require assumptions the evidence here does not close. The destination changes the accounting once more. A vehicle that merely crosses the 1 light-year line has achieved a different outcome from one meant to arrive there at a usable speed. Arrival requires the mission to shed the speed gained during acceleration. Braking, therefore, belongs in the same calculation as getting up to speed. Leaving it out can make a crossing time look like an arrival time, when the two describe different missions. The legal constraint supplies one boundary, and the propulsion concept supplies one possible source of momentum. Without a particular vehicle, speed, and mission outcome, nuclear is an engine family rather than a 1 light-year schedule. A propulsion claim first has to name the vehicle, because the engine family alone does not tell us which design is being timed. Different vehicles can place very different demands on the same broad kind of propulsion. Naming the vehicle fixes the subject of the claim, so its assumptions cannot drift from one design to another while the travel time stays unchanged. The assumed speed also has to be stated, or a travel time may look precise even though the velocity producing it is unclear. Once the speed assumption is visible, we can treat it as an assumption rather than as a result guaranteed by the engine label. The claim then tells us what the calculation begins with, rather than asking the name of a technology to carry the whole argument. Mission type is the third part of the test, and cannot be compressed into the word arrival. A flyby reaches the destination and continues past it. Braking asks the vehicle to lose enough of its speed to remain there, while capture asks whether that slowing ends in a usable relationship with the destination. An inhabited arrival adds people to the outcome, which makes it a different claim from an uncrewed vehicle merely crossing the same region. So a stated speed can support one mission schedule without supporting the others. If the calculation assumes a flyby, it cannot be presented as though braking, capture, and human arrival have already been included. Daedalus gives us a concrete case to which this test can be applied. The approved claim here is limited. Daedalus was an uncrewed concept study. That description tells us how to read what follows. We can examine its declared vehicle, its speed assumption, and its uncrewed flyby mission together, without turning the study into a forecast for a crewed ship that slows down and settles at its destination. It also prevents a separate claim about fusion power on Earth from being treated as a requirement for Daedalus, an equivalent achievement, or proof that the concept would work. The Daedalus study dates to the 1970s, and it described a particular kind of fusion vehicle, a 2-stage concept powered by deuterium and helium-3. Those details give the name a precise meaning. Daedalus does not refer to every spacecraft that might someday use fusion or to fusion propulsion as one broad family of ideas. It refers to this specified concept with its stated fuel combination and two-stage vehicle design held together as one proposal. Its mission category was just as specific. Daedalus was framed as an uncrewed flyby probe. No people were aboard in the study, and the probe was not being described as a crewed starship reaching a settled arrival. A flyby mission passes its destination rather than claiming the full outcome implied by stopping there. So any performance attached to Daedalus has to remain attached to that mission type. It cannot quietly acquire braking, capture, or the needs of a human crew simply because those would be required for a different mission. That is why the study tells us more than the phrase fusion ship ever could. An unspecified fusion ship leaves the vehicle class and mission outcome open, so a speed claim can seem to cover several very different journeys at once. Daedalus narrows the discussion to a named vehicle study and a named result, an uncrewed probe flying by its destination. We can then ask whether a claim belongs to that model without letting it drift into a claim about every possible fusion design. The engineering detail also has a firm limit. A design study can specify a vehicle without proving that the vehicle was built or flown, and Daedalus must not be treated as either. Its two stages, fuel choice and flyby mission, make the model concrete enough to examine. They do not make fusion propulsion available, nor do they amount to a finished design for human interstellar travel. When its stated target speed enters the calculation, the label stays with it, Daedalus, an uncrewed flyby concept. Only then do the vehicle, the speed assumption, and the mission describe the same trip. With that label in place, Daedalus has a specific target to work from: 0.12 times the speed of light, or 12% of light speed. That figure belongs to the Daedalus concept. It is not a speed that fusion propulsion in general has already achieved, and it is not evidence of an engine ready to carry people between the stars. It is the study's stated target for this particular uncrewed vehicle. Now the fixed ruler of 1 light year can be applied. Light covers that distance in 1 Earth year by definition. A vehicle moving at 12% of light speed covers 0.12 of that ruler in each Earth year. Divide 1 light year by 0.12 light years per year, and the result is 8.33 Earth years. The units cancel cleanly, leaving time. That answer describes constant cruise. It assumes the vehicle is already moving at the target speed at the start of the 1 light year crossing, holds exactly that speed across the entire distance, and reaches the far end without any part of the ruler being used to change its motion. Under those conditions, 8.33 years is the crossing time given by the arithmetic. A launch does not fit inside that division. Neither does the time needed to accelerate from rest to 12% of light speed. If the trip requires the vehicle to slow down at the destination, the braking period is outside it as well. During acceleration or deceleration, the vehicle is not spending the whole interval at the constant speed used in the calculation, so a complete mission clock cannot simply inherit the 8.33-year result. The same boundary applies to people. The division says nothing about crew protection, a working habitat, or the conditions that would keep humans alive through the crossing. Those requirements are absent because Daedalus was framed as an uncrewed flyby concept, not as a human transport whose full journey had been timed. Route choices are absent too. The ruler here is exactly 1 light year, with no mission path added to it. That mission description changes what 12% of light speed means. Project Daedalus was framed as an uncrewed flyby, so its speed belonged to a probe designed to cross the target's vicinity while still moving. It was never presented as a crewed ship that would arrive there, slow down, and remain. A flyby can still accomplish the mission it was designed for. The probe reaches the region around its target and passes through it without taking on the separate requirement of staying nearby. Calling that a failed arrival would judge the study against an objective it did not claim. The fast crossing and the settled arrival are different outcomes, even if both begin with the same distance and the same top speed. An arrival, therefore, needs another part of the design. The craft has to remove the velocity that carried it across interstellar space. A calculation based on 12% of light speed does not say how that braking happens, how long it lasts, or what system performs it. Those questions cannot be answered by taking the flyby time and simply adding a destination. The arrival model cited for this issue uses its own stated photon sail assumptions. It does not supply a completed braking design for Daedalus. Putting people aboard adds requirements that propulsion cannot settle. A human habitat would have to keep its occupants alive throughout the crossing, with life support systems that continue working for the mission's full duration. Experience with recycling aboard the International Space Station can give bounded evidence about parts of that problem. But it does not become a finished interstellar habitat merely because the vehicle can reach a high speed. Shielding remains separate as well. Radiation evidence can describe the danger a crew must be protected from, yet it does not provide that protection or tell us how a Daedalus-like craft would carry it for an interstellar mission. So the same 12% figure can describe a valuable probe flyby while leaving a human arrival unresolved. It is a conceptual speed attached to a stated mission, not a prediction that the needed propulsion, braking, habitat, and shielding will be ready on an operational date. That distinction changes what the Daedalus numbers can tell us. The material presented through the IAC treats interstellar propulsion as physically possible in principle, while also treating the engineering and economics as difficult. Those statements belong together. A proposal can obey the physics used in its calculations and still be far from something people know how to build, pay for, and operate. The calculated crossing time describes what follows if the proposed architecture performs as assumed. It does not put that performance on a calendar. A design study is valuable because it makes those assumptions visible. It can set out what the engine must do and trace the load paths, the routes by which forces would pass through the vehicle. That lets engineers examine whether the parts of the proposal fit together on paper and where the design carries demanding conditions. The study can then reveal which results depend on which assumptions. If an assumed performance changes, the consequences can be followed through the model instead of being hidden inside a single impressive speed. But a connected model is not an operating engine. Calculating how a proposed system would behave does not demonstrate that its engine has been built, nor that anyone has run it under the conditions the design requires. Engineering difficulty remains between the calculation and the machine. Economic difficulty remains there too, because a physically allowed design is not automatically one that can be developed and supported. The study gives us a specific account of the work the architecture would have to carry. It is not evidence that this work has already been completed. The source boundary becomes even tighter when the passenger is human. The approved material gives no generic fusion speed for a crewed mission across 1 light-year. Daedalus's target, therefore, cannot be turned into a standard performance figure for any vehicle described as fusion-powered, and its calculated travel time cannot become a promise of a 5 to 10-year crewed trip. It belongs to that conditional, uncrewed flyby model. A human mission would still have to carry the propulsion, braking, habitat, and shielding requirements left outside that model, without any approved operating date supplied here. The number still describes the model, but only as a result inside a defined architecture. An external directed energy design changes the architecture itself, which means its claims must be tested on their own terms. Breakthrough Starshot starts from a different division of labor. Its concept describes gram-scale robotic nanocrafts rather than a vehicle carrying people across interstellar space. That payload class changes what the propulsion system has to move, and it removes the habitat, shielding, and other crew requirements that a human mission would have to take along. The comparison with a crewed rocket has to begin there before any proposed speed is attached to it. A rocket using carried propellant must accelerate its payload along with the propellant it has not yet burned. The stored means of gaining speed is part of the mass that the propulsion system must keep pushing. Starshot shifts that energy source away from the craft. After launch, the nanocraft would receive momentum from a directed energy beam, so it would not have to carry the system supplying that energy as onboard propellant. The beam acts on a reflective sail through photon pressure. Light striking the sail transfers momentum to it, while the beam continues to supply energy from outside the craft. The sail is therefore the surface that couples the distant energy source to the small payload. This is not a tiny rocket with its fuel removed. The sail and the directed beam belong to one proposed propulsion architecture, even though they are physically separated. That separation is what makes a very low-mass robotic craft conceivable. It avoids one burden faced by carried propellant designs, making the vehicle accelerate an onboard energy supply that has not yet been used. But the burden has not vanished. It has moved to a large external system that would have to generate and direct the beam with the required precision while the sail responds to its pressure. So the Starshot concept is an exception to one rocket constraint, not evidence that every part of an interstellar mission has been solved. The approved program description does not establish a completed beam facility, a demonstrated launch system, successful passage to another star, or a spacecraft able to carry a crew. It defines a proposed route for accelerating gram-scale robotic nanocrafts. Any high-speed figure for that route still belongs to the proposal and has to be read within those limits. The published Starshot system model gives that proposed beam and sail architecture a specific speed target, 0.2 times the speed of light, or 1/5 of light speed. This is the model's point design, a defined case in which the parts of the concept and their assumed performance are considered together. It gives us something more precise than the broad idea of laser propulsion. We can place one stated design case on the same 1 light-year distance used for the earlier vehicles. But 0.2 C is an input to a proposed system model, not a speed that Starshot has reached in flight. The point design describes the performance the concept is built around under its model assumptions. It does not report an operating spacecraft, a verified launch result, or a measurement returned from an interstellar mission. That distinction changes the way the number can be used. We can ask what follows if a craft travels at the target speed, but we cannot present the answer as a record of what an existing craft has done. With that condition kept in place, the comparison becomes direct. The common distance is 1 light-year, and the proposed velocity is 1/5 of light speed. Dividing the distance by that velocity gives a conditional crossing time for the model case. It tells us how long the distance alone would take at a constant target velocity. It does not turn that crossing calculation into an arrival at another star, and it does not establish that the acceleration system needed to produce the velocity is ready to operate. The object moving in this concept also remains a gram-scale robotic craft. The headline speed does not belong to a crewed ship, a large scientific spacecraft, or every possible laser sail. It belongs to the program's proposed nanocraft class within this particular system design. That small mass is part of the case being analyzed, so the speed cannot be detached from it and reassigned to human transport. With that small craft and proposed speed held fixed, the division is simple. A light-year is the distance light travels in 1 Earth-year. A craft moving at 1/5 of light speed covers, in each Earth-year, 1/5 of that distance. It therefore takes 5 Earth-years to cross 1 light-year, provided it can coast at that constant speed for the whole crossing. The 5-year result comes from the distance divided by the proposed velocity. It is ideal arithmetic for the model, not a record of a flight that has already happened. The nanocraft is assumed to have reached 1/5 of light speed before this clock is applied, and the calculation does not establish that the system can produce or maintain that velocity. Crossing the distance also answers a narrower question than arriving for work. At the end of those 5 Earth-years, the craft has passed the point 1 light-year from where it began. The arithmetic says nothing about bringing it to a stop there. It does not show that the craft can survive the crossing, make a successful observation, or remain able to operate once it reaches that distance. Those are separate mission requirements, so the word crossing is doing important work. It describes how long the assumed vehicle takes to cover the ruler laid between its starting point and the 1 light-year mark. A stopped destination time would have to account for whatever the mission requires beyond constant coasting, and none of that is contained in the 5-year number. Communication adds another clock after the distance has been crossed. Suppose the craft reaches the 1 light-year mark and sends a signal toward Earth at once. That signal is light, yet it still has 1 full light-year to cover on the way home. By the definition of the distance, The return signal needs 1 additional Earth year to reach Earth. The craft's crossing would already be over, but Earth would still be waiting for the message. This delay does not alter the 5-year crossing arithmetic. It shows why that arithmetic cannot be presented as the duration of a communicating mission. 5 Earth years remains the shortest supported conditional crossing for this proposed 1/5 light-speed craft, while survival and useful operation at the far end remain unresolved. For that assumed crossing, the sail has to remain extremely light while intense directed light bears on it. The calculation depends on the craft gaining speed from that light, so the sail must keep reflecting it as intended and hold the shape the design requires. Adding mass to make the sail easier to manage would change the very assumption behind the proposed speed. A material that reflects well but cannot maintain its form would leave the same problem from the other direction. The crossing time tells us how fast the concept is meant to travel. It doesn't tell us how to build a sail that retains all 3 properties at once. Caltech describes this as a set of materials, photonics and structural challenges. Materials determine whether a very low-mass sail can meet the physical demands placed on it. Photonics concerns how the directed light and the reflective sail behave together, because that interaction is the source of the acceleration. Structural work has to preserve the sail's required form without turning it into a heavier craft that no longer fits the proposal. Progress on one challenge would not establish that the complete sail could make the crossing. The beam and sail would also have to be pointed. The proposal assumes that the directed light reaches the sail in the way needed to accelerate it. A speed written as a fraction of light speed does not supply that control. Pointing remains a mission question alongside the physical design of the sail. There must be a payload as well, even though every addition presses against the demand for low mass. That payload has to do more than survive the crossing. It must communicate, and it must perform whatever task the mission requires in the target system. The earlier return signal delay already showed that reaching the 1 light-year mark and reporting from it are different achievements. Here the distinction becomes physical. The sail, the pointing system, the payload, and its communications all have to work as one craft. None of these open questions proves that a laser sail is impossible. Together, they show why the 5-year result is still an assumed crossing time, rather than the schedule of an operational interstellar mission. That 5-year crossing describes how quickly the assumed craft covers the distance. The route still contains interstellar gas and dust. At a small fraction of light speed, meeting that material is no longer the same gentle interaction it would be for a slow vehicle. The relative speed makes those encounters energetic, and the effects continue to build as the craft crosses the space between the stars. That changes the engineering problem. Acceleration can give the sail enough momentum to begin the trip, but it cannot clear the route ahead. Gas and dust keep meeting exposed surfaces in flight. A single encounter is only part of the issue. The vehicle must endure the accumulated interaction over the whole crossing, with its sail, payload, pointing equipment, and communications still able to work when it arrives. Relativistic gram-scale spacecraft modeling gives one bounded way to estimate this effect. In a published case for a craft traveling at 1/5 the speed of light, or 0.2 c, the calculation produced roughly 0.5 millimeter of surface erosion, about 0.02 of an inch. That result belongs to the particular material in the model, the assumed grains in the interstellar medium, and the total column of material crossed along the route. Change those assumptions, and the erosion estimate can change with them. So the 0.5 millimeter figure is not a prediction for every fast spacecraft. It does not tell us that every light sail will lose the same amount of material, and it does not prove that a sail cannot survive. The model establishes a more limited point. At relativistic speed, the thin matter between stars can become a cumulative design constraint. Engineers would have to match the craft's materials and exposed surfaces to the medium assumed for its path, then determine whether the complete vehicle could remain functional through that exposure. A propulsion calculation therefore answers only the first requirement. It can describe how an assumed craft reaches its cruising speed and how long the distance takes at that speed. The crossing also demands a craft that survives what lies between its endpoints. Even if it reaches the far side intact, it will still be moving at 1/5 the speed of light. Arrival has another physical requirement waiting, removing that velocity at the target. Reaching the 1 light-year mark would satisfy a position condition. At some instant, the craft would cross the chosen point on our common ruler. The division of distance by speed can tell us when that crossing occurs, under the assumptions already made about the craft's motion. It cannot tell us what happens after the line has been crossed. If the craft is still moving at 1/5 the speed of light, it does not stay beside a target simply because it has reached the target's position. Its velocity is measured relative to whatever it is trying to approach. Unless that relative velocity is reduced, the craft keeps going. It may pass close enough to observe the target, but the encounter is a flyby rather than a settled presence nearby. Remaining there adds a separate requirement. The craft needs a braking architecture or some other specified way to transfer its momentum and energy away. That could be treated as its own design problem, without claiming that every possible braking method has already been ruled in or ruled out. The photon sail work applies to particular sails and particular target cases. It does not give every interstellar craft a universal way to stop. This leaves 4 different outcomes that can sound deceptively similar. A crossing means the craft reaches the marker. A flyby means it passes the target while continuing onward. Capture means a stated method has reduced the relative velocity enough for the craft to remain near the target. An inhabited arrival must do that and also meet the requirements of a working human system after the transit. Those distinctions let us compare missions without giving one mission the capabilities of another. A fast probe might be designed to return observations during a brief pass, and that can still be a successful result. A human destination demands more than the same speed with people added. Evidence about maintained systems can place limits around how people might operate, but it does not establish that a crewed interstellar arrival has been completed. So the arrival point is set by more than location. For a craft meant to remain, arrival occurs only after it has lost the relevant relative velocity. Any specific capture proposal must therefore say where that momentum and energy go. One published photon sail calculation gives us a concrete way to see what that requirement can do to a mission. The researchers modeled deceleration and capture for a specified sail and a specified target system. In other words, they did not begin with a speed and treat stopping as something the probe could arrange after it arrived. The sail, the target, and the desired captured orbit belonged to the same calculation. That calculation follows the exchange that any capture proposal has to account for. The incoming probe carries momentum and energy relative to the target. If the sail is to leave the probe captured rather than passing through, its interaction with light must transfer enough of both before the probe escapes. A higher arrival speed, therefore, does more than shorten the crossing. It also increases what the capture process must remove, while the target system can still act on the sail. In the cited Grafen-class scenario, the allowable injection speed for capture is far below 20% of light speed, or 0.2 c. One example from that model gives about 4.6% of light speed. The contrast is large. The faster figure describes a proposed flyby target, while the lower figure belongs to a calculation that asks the sail to decelerate and remain at the destination. Changing the outcome changes the permitted approach speed. 4.6% of light speed is not a general speed limit for photon sails. It comes from the particular sail and target assumptions used in that model. A different sail, a different star, or a different mission design would require its own calculation. And this paper does not show that photon sail capture has been demonstrated. What it provides is a conditional engineering case. Under those stated assumptions, capture cannot simply be attached to the end of a 0.2 c crossing. So a mission designed to stay may need to surrender some of the velocity that made the transit short, that can lengthen the travel time before anyone changes the distance at all. A flyby avoids that capture condition and can still gather observations during its pass, but its information has another distance to cross before people at home can receive it. That observation still would not be waiting on Earth as the sail swept past. If it were made 1 light-year away, the electromagnetic signal carrying it would have to cross that same 1 light-year in the opposite direction. The sail's trip and the signal's trip are separate stretches of travel, even though both belong to the same mission. Take the proposed starshot speed of 0.2 c. Under the ideal coasting calculation, a flyby could cross 1 light-year in 5 years. At the end of those 5 years, however, people on Earth would not yet have received a result from the far end of the crossing. A signal sent from there would still have 1 light-year to come home. The 5-year figure belongs to the sail's outward crossing. It cannot also describe when Earth learns what happened at the target. This adds a delay to the observer's clock, not another demand on the sail's propulsion. The craft does not need to reverse course and carry its observations back in person. Electromagnetic signals make the return crossing. Even in the narrow case where the sail survives a flyby and records something useful during its pass, that information reaches home later than the event itself. You could be waiting on Earth while the encounter had already happened far away. It helps to keep 3 times apart. There is the time the craft spends crossing the distance. There is the moment the mission outcome occurs at the target, whether that means a successful observation or something less successful. Then there is the later moment when Earth receives information about that outcome. A short headline can fold these together, but the physics does not. The return distance alone tells us only how long an electromagnetic signal must travel. It does not tell us how much data the craft could send, whether Earth could detect the transmission, whether the communications link would work, or how good the observation would be. Those depend on a communications design that the distance ruler and the proposed 0.2 c system model do not establish. So even after adding the signal's 1 light-year path, we have calculated a waiting time, not proved that any message arrives. The same care applies when antimatter is called a perfect fuel. CERN explains the attraction in a very specific way. When matter and antimatter annihilate, almost all of the mass taking part is converted into high-energy particles. The energy is tied to the disappearing mass itself. That is why antimatter keeps returning whenever people discuss ways to cross interstellar distances. This gives antimatter an energy density far beyond that of stored fuels whose mass largely remains after their energy has been released. With annihilation, the amount of matter involved is directly connected to the energy carried away by the resulting particles. A small amount of annihilating mass can therefore represent a very large energy source relative to the same mass of a conventional stored fuel. That comparison is about energy packed into fuel, though. It does not give the ship a speed or tell us how long a 1 light-year crossing would take. For a spacecraft, released energy is only the beginning of the propulsion problem. The ship accelerates by sending momentum away in the opposite direction. High-energy particles produced in an annihilation have momentum, but the fact that they exist does not tell us that a spacecraft can collect them, control them, and send enough of that momentum into a chosen exhaust direction. An energetic event and a working engine are different physical claims. You can see the gap by separating the source from the machinery around it. Annihilation supplies the high-energy products. A propulsion system would still need a way to turn those products into controlled thrust, while the spacecraft remains part of the system doing the directing. The approved evidence does not specify such an exhaust design, so the energy density advantage cannot be converted here into a mission performance figure. Antimatter has earned its place in the discussion because its mass conversion gives it a genuine physical advantage, not because the name itself guarantees a fast ship. We can accept that advantage without assigning it a percentage of light speed, a crewed mission, or a crossing measured in months. Before any of those claims can be tested, we need to know how much antimatter would actually be available to release that energy. That question about availability changes the scale of the problem. CERN describes present antimatter production and storage in microscopic quantities, far removed from a reserve that could supply a spacecraft. The energy released by each unit of mass can still be remarkable. Yet that advantage remains theoretical for propulsion if the fuel cannot be gathered and held in the amount a vehicle would need. Energy density tells us what supplied antimatter could contain. It does not tell us that the supply exists. CERN makes the production gap concrete with an idealized example involving captured antihydrogen. Under the conditions in that example, a full year of capture would yield about 3 times 10 to the minus 20th kilograms. That is a yearly figure only within CERN's stated example, not a forecast for a factory or a general rate for all antimatter production. We also cannot turn it into a price or use it to calculate the fuel load for a starship. Its role is narrower. It shows the amount associated with present laboratory handling. Storage has its own figure. CERN cites a scale of around 10 to the minus 18th kilograms for charged antiparticles held in traps. This number describes a storage scale, so it should not be treated as another annual production rate. It also refers to charged antiparticles, while the earlier capture example concerns antihydrogen. Keeping those descriptions attached to their sources prevents too small laboratory quantities from becoming an imagined stockpile. The traps demonstrate that antiparticles can be held, while the cited amount remains microscopic rather than a vehicle-scale fuel reserve. So the quantity claim places a firm present-day limit beside the energy claim. Antimatter's appeal per unit mass does not make it available as spacecraft fuel now, because current production and storage operate at laboratory scales. That conclusion applies to current facilities. It does not prove that future production or containment must always remain at the same level, and CERN's examples do not supply a basis for projecting how such technology might grow. Even a future supply would leave the earlier propulsion problem waiting. Released energy would still have to be directed into controlled thrust without destroying the spacecraft that contains and guides it. Making and holding more antimatter would answer the fuel quantity question, but it would not answer how that energy becomes useful motion. Annihilation still doesn't provide an engine by itself. Among the products are high-energy pions and gamma radiation. They carry energy away from the event, but a spacecraft needs more than an energy release. To produce thrust, the vehicle has to control how energy and momentum leave, so the release pushes the spacecraft in a chosen direction. CERN describes the conversion of those pions and gamma radiation into useful energy as difficult. That difficulty sits between the event and the motion we want from it. An engine would have to take products created by annihilation and make their departure contribute to controlled thrust. Energy that cannot be handled in that way does not become useful propulsion merely because much of it exists. The design chain also begins before annihilation happens. The antimatter has to be produced, then contained, until it is meant to react. Those are connected requirements. Producing a larger supply cannot help a mission if the vehicle cannot hold that supply, while containment alone provides no way to turn it into motion. Neither problem can be removed from the engine and treated as someone else's finished component. After the reaction, controlled exhaust and shielding join the same chain. The exhaust system has to govern the outgoing energy and momentum well enough to create thrust. At the same time, shielding has to protect the vehicle from the consequences of the annihilation products. The required equipment then contributes to vehicle mass, and that mass belongs in any claim about what the propulsion system could move. Improving one part of that chain does not prove the rest are solved. This does not show that an antimatter propulsion system can never be engineered. CERN's evidence gives us a narrower boundary. Converting the annihilation products into useful energy is difficult, and the cited material does not provide a demonstrated engine, a solved way to control the exhaust, a safe crewed vehicle, or a speed. Until production, containment, exhaust, shielding, and vehicle mass work together in one design, antimatter remains an energy source rather than a complete answer to the travel time. And because the evidence does not give us a speed, it does not give us a travel time either. The inherited claim that an antimatter ship could cruise at 70 to 80% of light speed is unsupported by the approved research. So is to claim that it could cross 1 light-year in a matter of months. Dividing the distance by a chosen speed can produce a tidy answer on paper, but the calculation cannot tell us whether any antimatter vehicle could reach that speed, hold it, or arrive safely. A defensible timetable has to begin with a defined vehicle. We would need to know what payload it carries and how the energy source fits into the ship's total mass. We would also need an acceleration history, because a ship does not leave Earth already moving at its cruising speed. The time spent gaining speed is part of the trip. A mission plan must then account for shielding and for braking at the destination. Without those pieces, the percentage of light speed has simply been placed into the equation as an assumption. Antimatter adds unresolved requirements of its own. The supply has to exist, remain contained, and release energy through a conversion system that can direct enough of that energy into thrust. That system and its protection have mass, as do the payload and the equipment needed to slow down. Each part changes the vehicle that the energy source must move. Until those parts are specified together, high energy density cannot be turned into a source-backed acceleration schedule. It tells us something about the fuel, but not how a complete ship moves across 1 light-year. That is the limit of calling antimatter a perfect fuel. The phrase can mark an imagined upper boundary for the energy source, yet it does not license a generic crossing time for a vehicle that has never been defined. We can still assume a coasting speed later, if the purpose is only to compare clocks. At a stated hypothetical speed, relativity can tell us how much time passes on Earth and how much passes for the traveller. But that clock comparison begins after the speed has been assumed. It does not supply the engine, the acceleration, the shielding, or the brakes, and it does not turn the assumption into an antimatter mission. Once a coasting speed has been assumed, the clock calculation can begin, but it needs a point of view. Suppose we choose the frame in which Earth is at rest. In that Earth frame, coordinate time is the elapsed time assigned between departure and arrival. It belongs to the system of distances and times used by observers at rest in that chosen frame. So when we say how long the crossing takes according to Earth, we mean this Earth frame coordinate time. The traveller carries a different measurement. A clock on the craft follows the craft itself from the departure event to the arrival event. The elapsed time shown on that clock is proper time, measured along the craft's path through space-time, or its world line. The traveller does not have to calculate this reading from Earth's clocks. It is the time accumulated by the clock beside them as the craft moves. These two readings describe the same departure and arrival, but they measure elapsed time along different paths. Neither one is an illusion, and neither fixes an error in the other. Relativity requires us to say which quantity we mean. Earth frame coordinate time answers how much time separates the events in the selected Earth rest frame. Craft proper time answers how much time passes on the moving traveller's own clock. At speeds far below light speed, the difference can be too small to notice in daily life. At a sufficiently high stated speed, it cannot be ignored. That difference has direct experimental support. Storage ring experiments test time dilation with fast-moving particles, comparing the time associated with their motion against the time assigned in the laboratory frame. The measured result follows the relativistic distinction between coordinate time and proper time. This is evidence for time dilation itself, not evidence that anyone has built a craft capable of crossing interstellar space at such a speed. The clock calculation, therefore, remains tightly bounded. It can tell us what Earth clocks and a traveller's clock would record after we supply a hypothetical velocity. It cannot supply the engine, the energy, an acceleration history, protection from the environment, or a way to slow down at the destination. With that limit left in place, we can choose an idealized speed close to light and ask what each of the two clocks would show. Suppose, then, that the craft is already coasting at 0.999 times the speed of light across 1 light-year, measured in Earth's rest frame. At that speed, the Lorentz factor, called gamma, is about 22.366. It relates the elapsed time on the moving craft to the coordinate time measured on Earth. From Earth, the crossing takes about 1.001 years. It is slightly longer than 1 year because the craft is travelling just below light speed. The 1 light-year distance has not changed in this frame, and the craft never reaches or exceeds the speed of light. The clock aboard the craft gives a very different answer. Proper time is the time measured along the traveller's own path, so we divide the Earth frame interval by the Lorentz factor. About 1.001 years divided by about 22.366 gives roughly 0.04476 year. On the traveller's clock, that is about 16.35 days. Those 16.35 days and Earth's 1.001 years belong to the same ideal crossing. They are two valid elapsed times for the same departure and arrival, measured along different paths through space-time. The short reading aboard the craft does not shorten the Earth frame distance, send information faster than light, or make fewer days pass on Earth. It changes how much time the traveller experiences once the extreme coasting speed has already been supplied. Special relativity can tell us what the two clocks read if a craft is already moving at 0.999 times light speed. It cannot tell us how to build such a craft, accelerate it, protect it during flight, or slow it at the destination. And the calculation includes no energy requirement, reaction mass, shielding, or vehicle design. So 16.35 days is a proper time result under an ideal velocity assumption, not a forecast for a human mission. The speed remains something the calculation asks us to grant. That granted speed has to come first. The traveller's 16-day reading appears only after we specify a craft moving fast enough for its proper time to differ from Earth's. Time dilation describes the relationship between those clocks once the velocity is already there. It does not push the craft to that velocity. A shorter reading on the traveller's clock is therefore an effect of the motion, not a way to create the motion. Nor can that clock affect pay the energy bill. It supplies no energy to the vehicle and no reaction mass for an engine to throw away. If a rocket carries its own propellant, the ideal rocket equation still connects the maneuver it must perform with the mass of propellant it must carry. Asking for a larger change in velocity changes that propellant problem. The traveller experiencing less time afterward does not change the equation. The clock can tell you how much time passes aboard the moving craft, but it cannot fill a tank or provide the force that empties one. An externally driven vehicle would arrange the payment differently. Energy or momentum could be supplied from outside rather than stored entirely aboard the craft, so the ideal rocket equation does not describe every part of that design in the same way. Even then, an outside system must still give the vehicle its velocity and keep the mission on a workable path. Time dilation contributes neither the drive nor the route. And crossing 1 light year is not the same as arriving somewhere and staying there. A craft moving near light speed carries kinetic energy and momentum that must be transferred away if it is to remain at the destination. That requires a braking architecture with constraints of its own. A proposed photon sail capture model is one example of how deceleration might be arranged, but its result belongs to that particular model. It is not a universal speed limit for every vehicle. So the 16-day personal clock result remains valid under its stated assumption, while the physical mission still has separate payments. Something must accelerate the craft, something must supply the energy or momentum, and something must slow it again. Once the velocity is treated as a real environment rather than a number handed to the clock calculation, the ship also has to endure what travelling through space at that speed would bring. At relativistic speed, the thin material between stars becomes part of the engineering problem. Model-dependent work on gram-scale craft finds that collisions with interstellar gas and dust can be energetic and cumulative. The exact erosion or impact damage cannot be carried over to every vehicle because it depends on the material, speed, and path being modelled. Even so, the craft must meet the gas and dust along its route, and its materials and impact protection must tolerate those encounters. An ideal calculation that divides distance by cruising speed leaves all of that outside the equation. Radiation creates a separate set of risks. Deep space particle environments can affect a crew, damage electronics, and alter materials. There is no single dose or shield value that settles this for every mission. Exposure depends on the route and duration, while any estimate also depends on shielding, the solar cycle, and the biological model used to translate an environment into risk. Shielding choices bring trade-offs of their own, so saying that a craft is shielded does not demonstrate that its crew and systems are safe. Gas and dust describe encounters produced by motion along the path. Radiation describes a particle environment and the protection required within it. The passenger's shortened time does change one part of this problem. If the onboard interval is 16 days under the stated relativistic assumption, the crew experiences that interval rather than the much longer time recorded from Earth. But the favourable clock result does not remove the material ahead of the craft. It does not select a safer route, determine how much shielding is needed, or prove that the hull and electronics will survive. The Lorentz factor changes the interval on the passenger's clock, while the physical interactions continue. Extreme speed is therefore a human system exposure problem as well as a travel time calculation. A credible vehicle would need its gas and dust response, radiation protection, route and mission duration assessed together, while preserving the distinction between the two hazards. The available models identify constraints. They are not a complete design or safety certification for a human interstellar mission. Proper time can give the travelers fewer days between departure and arrival, but it cannot shelter them from the environment crossed during those days. A crew cannot answer a long travel time simply by loading all the water it might use before departure. Every additional supply has to travel with the habitat, so carrying more water also adds to the mass that must be moved. The alternative is to recover water after use and return it to the crew again and again while the mission continues. NASA has demonstrated how far that approach can go aboard the International Space Station. Its environmental control and life support system reached a milestone of 98% water recovery. In practical terms, recovery reduces the amount of replacement water that has to arrive from outside. That is a real operational achievement on a crewed spacecraft, and it changes the problem from storing the full requirement at launch to keeping a recovery system working over time. The percentage alone does not do that work. Hardware performs the recovery, draws energy, and has to be monitored while people depend on it. Components need maintenance, and the crew and teams supporting them need the ability to find a fault and repair it. Reducing resupply mass therefore exchanges some of the burden of stored water for machinery, power, observation, upkeep and repair capacity. A mission lasting far longer than the equipment's designers would have to preserve those capabilities as part of life support, because recovered water remains available only while the system continues to operate. The International Space Station also sets a firm boundary on what this demonstration establishes. It is a maintained program supported from Earth, with people and supplies available beyond the station itself. It is not a closed habitat shown to sustain itself for several centuries without resupply or outside intervention. The 98% milestone does not prove that such a habitat is impossible. It simply does not demonstrate one. For an interstellar crew, the question becomes whether recovery hardware can remain powered, watched, maintained, diagnosed and repaired for as long as the travelers need it. Even complete success with that water system would settle only one part of survival. Radiation and the shielding needed against it remain outside the resource loop. Even if the water keeps circulating, the habitat still has to carry people and machinery through a particle environment. The deep space radiation literature treats this as a distinct problem for crew health, electronics and materials. It is separate from the impacts of interstellar dust and gas against a fast-moving ship, and has to be assessed on its own terms. Shielding sounds like a single item that could be added once the rest of the ship is designed. Galactic cosmic rays make that much less simple. The literature identifies trade-offs involving both the mass of the shielding and the materials used. Extra shielding becomes part of the vehicle that the engines must accelerate, the power system must support, and the crew must maintain. It cannot be treated as weightless protection with no effect on the mission design. There is also no universal risk number that can be carried unchanged from one proposed voyage to another. Exposure depends on the route through space, the solar cycle during the trip, and the time spent traveling. It also depends on the shielding configuration rather than the mere presence of shielding. Then biological models are needed to interpret what that exposure could mean for the crew. Change any of those inputs and the assessment changes with it. That conditional answer sets a useful limit on what the evidence can support. The cited work identifies risks and design trade-offs. It does not certify a crewed interstellar vehicle, predict a particular illness, or supply one dose that is always safe or always fatal. A mission proposal would have to state where the ship travels, when it travels, how long the exposure lasts, what protection surrounds the habitat, and which model is being used to judge the biological result. Without those details, saying that space is dangerous has not yet become a design analysis. Water recovery and radiation protection place different demands on the same habitat. One keeps a needed resource moving through a maintained loop, The other asks whether people, electronics, and materials can remain functional in the conditions of that trip. For a voyage long enough to outlast its original crew, survival depends on managing supplies while preserving a workable environment for the generations that inherit the ship. The people who inherit that ship would also inherit every machine keeping it habitable. If a recycler, shield, power system, or part of the habitat failed, there would be no rapid resupply mission bringing a replacement, and no nearby team able to intervene. Repair capacity would therefore be part of survival itself. The ship would need systems that people inside it could understand, inspect, and repair, without waiting for Earth to solve the problem. That requirement extends beyond carrying spare parts. Maintenance skills have to pass from the people who learned them to people born much later, and the knowledge behind those skills has to remain usable as equipment ages and crews change. A habitat can keep working across successive lifetimes only if its residents can preserve the ability to diagnose trouble and make informed repairs. Technical continuity depends on human continuity. The same duration creates decisions that machinery cannot settle. Communication delay means the community must govern itself while operating the habitat. Its members must decide how work and risk are handled, and the mission can continue only through their consent and some shared purpose for continuing it. Those conditions aren't decorative concerns to consider after choosing an engine. They arise because the people aboard must keep the habitat running through lives that the original crew will never share. None of this gives us a numerical probability that such a community would succeed. Operations on the International Space Station and evidence about radiation can show why maintained life support, repair, and crew protection are required. They do not amount to an experiment in which an isolated generation ship has operated across multiple lifetimes. There is no existing ship of that kind from which to calculate reliable odds, and the absence of that evidence does not mean social failure is inevitable. So the word us describes more than the number of passengers who leave Earth. It includes a continuing system that must preserve working equipment, practical knowledge, decision-making, consent, and purpose across generations. Speed and fuel can tell us how long a vehicle might take to cross 1 light-year. A human travel time also depends on whether the technical and social system can remain continuous for as long as that crossing requires. With us meaning a human system that continues through the trip, the time question separates into different kinds of answer. Voyager 1 gives us the demonstrated benchmark. Using its cited speed relative to the Sun, it would take roughly 17,600 years to cover 1 light-year, provided its speed and direction could be held. That figure is a conditional comparison. Voyager 1 is real hardware travelling outward today, but the calculation is not a forecast of its route or destination. At the other end is a proposed sail carrying a gram-scale payload and targeting 0.2 c, or 1/5 the speed of light. Divide 1 light-year by that assumed cruise speed, and the ideal Earth frame crossing time is 5 years. The arithmetic is sound within those conditions, but its meaning is narrow. It describes a small proposed sail during an ideal crossing. It does not include acceleration, braking at the far end, people, or a demonstrated arrival at rest. That leaves no single human travel time that can be supplied by naming an engine. A crewed mission would have to gain its velocity and then shed it, while also surviving hazards throughout the transit. Its life support systems would have to remain dependable for the required duration. If the trip extended beyond individual lives, the mission would also depend on the technical and social continuity we have been following. Maintained equipment and knowledge, with people able to keep the system operating across generations. Those requirements belong to one mission, so demonstrating only one of them would not demonstrate the complete mission. The answer, therefore, depends on the proof standard attached to it. Hardware already moving outward gives a 1 light-year comparison measured in millennia. A proposed ultralight sail can reduce the bare ideal crossing arithmetic to years. A demonstrated human arrival has no settled duration because no complete system has yet demonstrated acceleration, transit, braking, human support, and continuity together. Perhaps those open requirements can someday be made to work as one mission, but we cannot assign that result a generic travel time now. The light year remains the same fixed distance. What changes is whether the calculation describes crossing it, arriving after it, or sustaining people all the way through.